So what we're going to do is we're going to give 3 little mini presentations today, followed by a short panel question and answer. So we'll only take about 3 questions after each little speaker has done their mini presentation, and then we'll cut you off, do the next mini presentation, and then you can just hold all your questions till the final panel session at the end. Okay, so I'm going to get started here with Ralph. Take it away, Ralph.
All right, so as Wayne said, we're going to talk about CAD programs, which are cheap or open source, free. I'm going to start off talking about OpenSCAD, and I'm sure some of you have probably already heard of that. It's a completely free, open source 3D modeling package, and what's unique about it is it's actually a text-based tool. So you're not sort of using your mouse and dragging things around and going through menus and doing things. You have a text editor. That it's very simple language. I'll show you in a second. It allows you to create both parametric and what I call algorithmic models, so that you can have a variable defining the size of the robot, and just by changing that, the whole model can automatically dynamically correct itself. It works on Linux, Windows, Mac, and it's good for 3D printing, laser cutting, and building simulation models for URDFs or Gazebo or something like that as well. So some of you are probably familiar with tools like Mark's going to talk about 3D Fusion, 360, and SolidWorks. Great tools, but huge learning curve. This page here is every command there is in OpenSCAD. All you need to learn. So we'll go through a few of them quickly. As said, basically there you can start with 2D primitives like circles, squares, polygons, mostly in text. 2D outline you can then extrude it, either sweeping it through a curve or something to create a 3D, or just linearly extruding it. The key ones we'll talk about will be spheres, cubes, cylinders. They're the 3D primitives that virtually everything gets built out of. You assemble them together into blocks using various transforms, such as translate it, to position it in space, rotate it, scale it, etc. You can apply attributes like colors and offsets, some more advanced features, and then you can combine them together by union, difference. So difference is a key one we're going to use, where you might take one object and use it to cut a hole in another object. So drill holes and things like that, you can use a difference to create those type of functions. We said it's algorithmic and parametric, so you get a whole bunch of mathematical functions. So you can actually create equations to generate the parameters for the geometry, and a whole bunch of other more elaborate stuff we won't have time to go into here. So I'm going to start off very quickly. This is the UI. This is all there is to see. There's a text editor, a 3D view panel, and a status panel that just tells you what's going on, if you've got any errors or something in your code. The 3D panel, as you see, we can interact with that. It shows you real time what you actually modeled. You've got the standard orthographic projections, top, bottom, perspective, or orthographic. You can turn on some axes to see the orientation, put some tick marks to get a sense of scale. That's basically all there is. So what we're seeing here, first line of code I've created is a cube. So all you do is you type in cube, give it X, Y, Z, tell it you want it centered at the origin. If that's false, it puts the center of the origin at a corner. There's your first object. You've created a model in OpenSCAD. So we can do something else. Whoops, instead of that, I'll say no. You can change the size of it and get a flat cube. Let's add another object. We can create a cylinder. Get rid of the comment.
You got to comment out UB.
You have an oob object there.
There we go. So now we've got a cube and a cylinder together. Put 2 objects, they combine them into one object. We can do one more. Let's add a sphere. Okay, but they're all sort of crunched on top of each other. Not that interesting. So what if we say add translate? So it's now an operator. Now I can move upside down. Move it. What if I want my cylinder? We put different radiuses on the cylinder. So now I've got a little funky chess piece or something. I can also, I don't like it all being yellow, I can tell that I want this object to be red. Now I've got whatever sort of attributes. This could be a little tedious though, to have to type every single component all the time. So there's another method we can use. I'm going to try to type in here. So we mentioned that we have parametric, so there's some variables I've defined, dimensions I want to use. And now also, let's say I always want to have a green cube. So instead of having to type color, cube, maybe any other set of operators, I can now create my own module. And since we're robot builders, let's build a robot model. So we'll start by creating the base of a robot. And there's my green cube now called base, and you see that I've now invoked that in the model by typing base instead of one of the raw primitives. So because it's a robot, it needs wheels. So let's go ahead and define a wheel. I've got this backwards again. It's not a wheel.
But it's green.
There's a wheel. So now we've just used the cylinder to create a wheel based on the dimensions. Not a very interesting wheel, it needs an axle. So let's create a new cylinder, put that through, there's our axle. Right, let's say we wanted a wheel with a hole in it that we could put on a separate axle. So there we can use the difference operator. And that's going to say take the second cylinder away from the first cylinder, and now we have a hole in our wheel. Now, of course, now we need that other axle to put our wheel on, so I've created here a little axle with a hub on it. So we've added the cylinder and a sphere, we've moved the sphere to the end, and now I've got a definition of a wheel that I might put on a robot. So now let's have a look at how we build a fully built robot. Stand down for a second. So we'll create a new robot object, and in this one, instead of bringing in primitives, I can also bring in those other modules I've already defined. So there's my base and my wheel, but now we've also done it algorithmically. I've created a wheel once, but I've now wrapped this with a for loop, where the parameters in the for loop, the position, I've got to translate to move it to somewhere, and the parameters of that are defined by the for loop. So I can create 4 wheels algorithmically from an equation. We also rotate them so the hubs fit, left to right. So another thing we can do is, you notice we have these modules now also have parameters. So I could invoke multiple instances with different parameters, for example. And I'm going to use AS is for angular something. We'll go ahead and add a head since we're building a robot. It's upside down, so there's a little robot with a head on it. And for the head, we've created an equation using a math function, the sine of this parameter. So what does that do? Well, if I invoke it down here, it gives me the angle. If I put 0, it looks straight ahead. If I put a quarter, it looks to the side. If I make it negative, it turns the other way. And there's a really cool feature that you can do with parameters. There's a special hidden variable called $t for time. If I add that, and I turn on animate mode, I can now specify, let's say I want, what is it, 30 frames a second, and I want 100 frames. It now animates my model.
Nice.
So we can check motion. You can actually save these video out and create a video from the frame. So if you've got motion and moving parts, you can sort of simulate and animate that to see what's going on. So that's the most basic steps of what you might want to do. Let's have a look at what we can do in a more real world. So here's an example of a model robot that I actually designed, and you'll see the robot is actually sitting over there. It was designed using OpenSCAD. So what we've incorporated into this model, as we talked about, there's a bunch of parameters, so I can change the geometry at will. Something else we've done here, we've included other models. So you don't have to have just one big file, you can create a library of models and bring them in, incorporate it. So here we have the connect, and a modal library, a whole library of motors that I can specify and bring in and add to models, plus the mounting for the connect. And as well as bringing that sort of object in, we can also use existing STL files. So if you already have a model from another tool, or you download a model from the internet, I can import STLs and then wrap them in modules, and they look like any other part that I've built. So you see here I have the Jetson circuit board stuck on the back there. That's just from an STL file. Similarly, the Robo Claw sitting on the front of it. So that makes it versatile. You can build your own libraries, reuse parts, download objects off the internet. You don't have to create anything yourself on everything. So then, yeah, a whole bunch more complicated here as it goes in. We've got motors, we've got the base defined. So the base is basically, let's just look at that as a single object. Something I like to do once I've defined a bunch of modules, at the end of my file, I'll just list them all as separate functions, and you see this little asterisk says hide it. Don't just ignore this for now. But that means I can turn something on by just deleting that asterisk. And what was I looking at? I was looking at the robot as a whole. We can turn that one off. And now I get to just see the base part, so you can always explore that. Modules don't have to only be parts. You can create modules that help you see the model in different ways, and I'll show a couple of examples of that in a minute too. But what's interesting now about this base, I'm not going to do it because it usually takes about 10 minutes to actually render it for some reason. But there's a mode now with this base. I can use this extra statement called project, which actually takes an object, projects it onto the ground plane, and turns it into a 2D drawing. And from that, I can then export that as a DXF, which I can send to my laser cutter. And this is the deck that you'll see on that robot that was generated from the laser cutter by exactly doing that. The other thing you might want to do is, instead of the base, let's have a look at our motors. So I've got a subset of parts here, which is just the motor mounts and the motors, and they're all arranged nicely here. Oops, there's a center mode that repositions it for me. So this is great. I can explore the sub-assemblies I've made here, check that the holes all line up. And again, this is, I've created a special function. But something else I might want to do, each of these individual mounts has been made, and let's say I want to 3D print them. So I can use a smart function. I've passed the parameter. Now in that motor module, I've said, if this is true, align them in a different way, throw them, hide the real parts, just give me the 3D printed parts, mostly compacted them on a zero plane that I can just export that as a single STL and have it 3D printed. So I think that's, in a nutshell, with the time running out, most of the key features that I wanted to talk about. So I'll just go back to the slides here, and things I didn't talk about, things you can create not only parts but operators. So a module, there's a special magic parameter called children. So instead of having a module that contains parts, you just put this magic value children. Maybe the rest of that is a bunch of translates. Maybe there's some parameters that you're calculating. And if I can use my module as if it was a translate function, put it in front of other objects and have it apply whatever transformations it has to the objects that I make its children by just putting them next to it. So that's usually you can build libraries of tools. So that way you can build tools like drill patterns. You can say, here's an object that calculates the position of my drill patterns, and then I can apply it to different surfaces that have to have the same drill holes that they can always line up because they've been used. And you can create libraries of these sort of functions. You can download stuff. A few things to note, their trig functions use degrees and not radians that you might be used to. I always recommend using millimeters. The units are kind of arbitrary, but if you just assume I'm typing millimeters, then it exports nicely to 3D printers and stuff like that. There's some links here, we can share the slides and go over it. So, I'm probably not on the internet here, so I don't have the downloads. There's a pretty good website. Yeah, it's not on. Very well documented, all of the keys. There's lots of examples, show you example scripts and stuff like that. So I think that was OpenSCAD in a nutshell. So. A bunch of other examples of parts that I've printed over there if people want to actually have a look at how stuff came out. Yes?
I just wanted to give a quick testimonial because I took the class at Tech Shop where they showed you how to use, I think it was the Autodesk AutoCAD software, and it was like hours to learn it. And then when I wanted to make a simple part, it was just a cube subtracted by another cube for a little U-shaped bracket. It took me hours to power it up, to download everything. Someone told me about OpenSCAD, never heard of it before, but I had downloaded it, looked at the tutorials, it was so obvious, and had my part done in 6 minutes flat.
Yep.
So it's extremely easy, and it looks exactly like C code, which was good for me.
Similar, yeah. And so you can, I think, some people at Wayne or other people have actually written Python programs that generate OpenSCAD scripts. So, okay, well, thank you. We'll have more. So I think we're going to have
One more
one
question.
more.
Real quick, you were setting the angle of the head there.
Right.
Is that angle then exported globally? You can use it in other modules? I saw how you pass parameters into the module.
Right.
Is there a way to get variables out of the module?
What you can do, if you want to do something like that, you can actually define a function. So instead of having the equation embedded inside the module, I can create a global function that takes the parameter and returns a value, and then I can reuse that function in other places that I would want. So there, you can put a library, create a library of functions, and then invoke them within different parts within the script. So, okay, I'll hand it back to Wayne to pass on to the next victim.